All right. So, what we're going to talk about today is modeling flow over a raster. So, we've talked previously about how we can model a particular path over a raster from one point to another. Now, what we're going to do is rather than having a defined start and stop point, we're going to look at how something would just flow, in this case, over a digital elevation model. And so, in order to properly model flow, there's a couple of things you have to do sort of pre-processing, which we're not really going to talk about. But basically, you just have to make sure you get what's called a hydrologically stable DEM or a hydro DEM. And that basically just means that you have a digital elevation model that has all of the little divots and errors in it corrected so that when you're calculating flow, you don't end up with things pooling in erroneous pixels. But once you're sure that you have a good DEM, the first thing you're going to do is you're going to take that DEM and you're going to convert it into what's called flow direction. And this flow direction is going to look very similar to how we calculated the cost distance, how we went from cost distance to cost direction. It's going to look very similar to that. Then you're going to take that flow direction layer and you're going to convert that into what's called flow accumulation, which is going to basically account for how many pixels or cells would flow into any given cell. So the cell value of the flow accumulation layer is literally the number of other cells that flow into it. And then once you have that flow accumulation layer, you can then move on to do all kinds of flow modeling. So the flow modeling approach we're going to focus on is going to be stream delineation. You can also do watershed modeling and point flow for point source pollution, but we're going to focus mostly on stream delineation because the first two steps are really the bulk of the work here. So assuming that we have a high quality DEM, the first thing that we have to do is convert that DEM to a flow direction raster. And the way we do that is we look at, for a given cell, we look at all of its neighbors. We calculate the slope from the given cell, which is going to be the 2 cell. From the 2 cell, the slope to the from cell. So 2 cell, from cell. We're going to calculate the slope as rise over run, which is the difference in elevation between the two cells divided by the distance. Now, in this case, distance is going to be the same as we talked about when we talked about path modeling, where we're measuring from the center of one pixel to the center of another pixel. So we're going to be using that cell size. Or in the case of diagonal pixels, we're going to be using that cell size with that 1.41 scalar to account for the fact that we're moving at a diagonal, right? We're basically calculating the difference in elevation divided by the distance. And in the case where, since we're trying to model flow, right, things tend to flow down, right? So anytime we have a negative slope, meaning that the difference in elevation slopes downward from the cell that we're in to the cell that we're going to, right? That means that any sort of fluid would flow down between those two cells. And the way that we handle flow direction is we basically just look and say, okay, well, of the 8 neighboring cells that we have, if any, which one has the largest negative slope, right? Because that's going to indicate, at least in this, with the way that we're modeling it here, that, hey, it's going to flow from this cell to that cell because the slope between them is the most negative, meaning it's the steepest downward from the cell that we're currently in. So what I want to do is I want to go through some examples of what that looks like in terms of calculations and figuring out how we assign the flow direction. So, keeping in mind we have our equation here, let's go ahead and focus on what the flow direction would be for this pixel right here, this 97. So in order to figure out what the flow direction would be for this, right, we pull out its neighbors. So that's these 8 surrounding pixels. So that's what this is here. And we're going to say, given this elevation value of 97 and the elevation values of these surrounding pixels, what direction is fluid going to flow across or from this pixel? And again, right, slope is just the rise over the run, which is the differences in elevation divided by the distance. So let's go ahead and first consider the slope going at a diagonal from 97 to 85. So the slope going this way at this diagonal here. So what we're going to do is we're going to calculate the elevation to, elevation from, which is 85, minus the elevation to is 85. So going from this pixel to this pixel, right? So we're going from 97 to 85. So the elevation to is 85 because this is the 2 pixel because we're going to this pixel. So it's 85 minus the elevation from, which in this case is 97, right? Because that's the pixel that we're focused on, divided by distance. Well, because we're going at a diagonal, right, we have to include that scaling factor. This is the scaling factor to deal with the diagonal pixel, times the cell size of the image, which in this case, right, the cell size for everything is 30 meters, right? So it's the elevation where we're going minus the elevation where we came from divided by the distance between them, which is the cell size, and in the case of a diagonal, multiplied by the scaling factor. So what do we get if we do the math on that? Well, we get a value of negative 0.283, meaning the slope between this pixel going from this pixel to this pixel gives us a value of negative 2.83, meaning it is a negative slope, meaning that any fluid on this pixel could flow into that pixel because it's downhill. So let's talk about going from this cell going north. So we're going to look at this neighbor up here. We're going to plug in the exact same equation. The elevation from, or the elevation to, minus the elevation from. So it's 87 minus 97 divided by the distance. Now in this case, because we're not going at a diagonal, we just use the cell size. Right, so 87 minus 27 gives us negative 0.333. Again, meaning that liquid would flow from this cell into this cell potentially. Right? And so as an exercise, I would encourage you to pause the video, go through and figure out these two cells, which I've already pre-calculated. Because what I want to do is I want to look at what happens when we reach the cell that is the lowest value, this 55 here. So going from 97 to 55. Right, so again, right, we take the elevation of the cell we're going to, which is 55, minus the elevation of the cell we're coming from, which is 97, divided by the distance, which again, 30 meters is coming from the cell size of the image, times, because we're at a diagonal, times the scaling factor here, which gives us negative 0.993, which so far of the values that we've calculated is far and above the most negative. So we record that. We keep going around, right? And we get to the first instance where this value is now higher than this value, right? 98 is higher than 97, even if just barely. And so we do the calculation again, right? So we take the pixel value of the cell we're going to minus the elevation that we're coming from. So that's 98 minus 97 divided by the distance, which again is the cell size, which is 30 meters, times the scaling factor because we're going at a diagonal. And what we end up with in this case is the first time we have a positive slope, right? Zero, even if it's just barely a slope, right? 0.024, meaning, right, that this slope here is actually sloping upward, meaning water would actually flow down into here. Right? This is an upward slope, meaning that we do not consider it as even a possibility because it's not even negative. Okay? So once we calculate all of the slopes, so each one of these values represents the slope going from the center pixel to whichever pixel we're talking about. So the slope from here to here is negative 0.26. And again, I encourage you to pause the video and calculate those if you aren't fully feeling confident with how we got those. What we have to do now, though, is figure out what direction we're going to send the fluid, right? So starting from this cell, what direction is the fluid most likely to go? And we're going to do that by picking the most negative slope. So what of these values is the most negative slope? Well, the most negative slope in this case is going to be the negative 0.993, meaning that it's going to go from the center pixel down and to the right, right? So this value here is our most negative, right? Our largest negative. So now that we know what direction it's going to go, we need to figure out what we're going to do in terms of figuring out what value we actually assign to the pixel, right? Because we know it's going to go from here to here, but what value do we actually put in our flow direction? Well, this is going to work in much the same way that it worked when we did the modeling paths, where what we have is a set of coded values. So this table here is coded values, meaning that if we assign the pixel a value of 1, that means that the water is going to flow to the right. If we assign the pixel a coded value of 32, that means that the fluid would go from this pixel up to the left, right? A value of 16 means it's going to go from this pixel to the left. A value of 128 from this pixel to the upper right, and so on. Okay? So given that our most negative slope, this negative 0.993, is down and to the right, what coded value are we going to use? I encourage you to pause the video, think through, what coded value would indicate that we would leave the cell going down and to the right. Well, we would end up using 2, right? Because again, this most negative slope is down and to the right. The coded value 2 means that we would leave the cell going down and to the right. So that means that we would give this middle pixel, so that the pixel that we were most concerned with, would end up getting a coded value of 2, meaning we would leave from this pixel down and to the right, because again, these are coded values. Much the same way we used coded values for calculating the cost distance direction raster. So let's look at another example of figuring out which one of the flow direction coded values to use. So in this case, we're looking at the pixel 96. So we've shifted over one, and we're looking at a new set of cells surrounding this 96. I've already calculated the um, slopes here. And so the question then becomes, which direction do we go? Well, again, right, we're going to look for the most negative slope. The most negative slope in this case is going to indicate that we should go to the right from this 96 to 54 with a negative 1.4. So again, right, 96 to 54, negative 1.4. In this case, that means that we're going to be going to the right. So we're going to leave 96 and go to the right. So pause the video for a second. Think through which one of these coded values here means that we would leave the pixel and go to the right. Well, again, right, because our most negative slope is negative 1.4, that means we leave 96 and go to the right. Because we leave 96 and go to the right, we would assign that center cell the coded value of 1, right? Because a coded value of 1 means, hey, we're going to leave and go to the right. So I want to take a second here and I want to outline why we use slope instead of just using the direction of the lowest pixel. And that has to do with the diagonals, right? Because if values are close together, the diagonal will actually have a more gradual slope because it's got more distance because of that scaling factor, right? So two values being equal, the diagonal and a non-diagonal, the diagonal will actually have a less steep slope. So that's why we use slope and why we go through the hassle of calculating slope as opposed to just using the direction of the lowest elevation, because the diagonals actually have a different slope due to that scaling factor. So even though the diagonal might be slightly lower in value, a non-diagonal might still have a steeper slope. Okay. So let's go ahead and finish up the flow direction raster. So again, taking a neighborhood of values, calculating the slope from the center to all of its neighbors, figuring out which direction is the most negative slope, applying that direction to the coded values to figure out what direction you would leave from the cell, and then assigning that value, that coded value, to the center cell. And so you'd end up with something like this. Zeros here indicate that you actually would not go anywhere because this is a lowest point and this is a lowest point. You would not have anywhere to go, so I gave them values of 0. Technically, that should have also been 0 as well. But anyway, so what we can do to sort of ease the interpretation for the next steps is we can actually take this flow direction raster, and just for the sake of visualization, we can replace the numbers with arrows indicating what direction you go from that cell center. So this image here, where I've indicated arrows for what direction you leave the cell, is exactly equivalent to the numerical coded values version. It's just a little bit easier to intuitively see what direction things are going. So again, your computer would be using the coded values, but in terms of explaining through the processes, I think it's a little bit easier just to use these visual arrows here. But again, a down and to the left, a down to the right arrow is the same as a coded value of 2. Okay, so once we have our flow direction layer, the next step is going to be to take that flow direction layer and calculate what's called a flow accumulation layer. And like I said before, with the flow accumulation layer, what we're doing is we're basically trying to figure out for a given cell how many other cells flow into it. And what that generally boils down to is figuring out for each cell which of its neighbors flow into it. And then if any of those neighbors have cells flowing into them, we want to carry over that sum as well. And we'll look at in a couple of examples and see what that looks like. That sort of cascading action, we'll sort of see what that looks like. Okay, so again, we're going to switch over to our arrow diagram just to make things a little bit easier. And what I want to do is I want to start with figuring out for this upper leftmost cell here, what is its flow accumulation, right? In other words, how many cells flow into this cell here? So take a second, pause the video, and look at the arrows and figure out how many arrows point directly into this cell. And that's going to be the flow accumulation for that cell. Right? Well, in this case, right, 2 cells flow into this cell. This one flows in from this direction. This one flows in from this direction. So the flow accumulation for this cell here is going to be 2. What about for this cell here? Take a second, pause the video. I know the answer is already here, but think about how many cells flow into this one. We know this cell flows over here, but how many flow into this cell? The answer to that is 0, right? 0 cells flow into here, right? Fluid will hit this surface, it's going to run this way, but there is going to be no new fluid coming in from any other cells, surrounding cells, right? And so I've gone ahead and I filled in some more of the flow accumulation layer, and we get to this one here. We get to this one right here. And I want you to pause the video, and I want you to think through, for this cell here, how many of its neighbors flow into it. Right, well again, right, just like the other ones we've looked at, in this particular case, right, there are no arrows pointing into it. None of its neighbors point into it. So this would also have a flow accumulation value of 0. So let's jump ahead a little bit, and let's jump to this cell right here. And this is the first time where we're going to have to think things through a little bit farther in terms of that cascading effect, right? So let's start by saying how many of its direct neighbors flow into this cell here. Right, take a second, count them up, right? This cell flows in from here, 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 and this cell flows in from here, right? So if we add that up, we get a total of 5 cells flowing into here, right? So we have these 5 cells highlighted in red, right, are flowing down into this cell here. But, right, this is a big but, right? If we look at this cell right here, you'll notice it also has cells flowing into it, right? And if you remember how we generate flow accumulation, right, these 2 points here, it's not just the neighbors that matter, it's how much flow the neighbors also are already carrying, right? So for this particular cell here, we can't stop, right? Because this cell right here also has its own flow, right? This cell has 5 cells flowing into it, but this cell has its own flow. So we have to figure out its flow, right, before we can figure out the final flow of the cell that we started with. Okay? So we still don't know what the flow accumulation is of our starting point. We had to go back 1 layer, and now we're trying to figure out what the flow accumulation is of this cell. So again, right, how many cells flow into this one, right? Given our visual diagram here, right, how many arrows point into this cell? Right, well, it's 5, right? This one comes in from this diagonal, this one comes in from this diagonal, this one comes in from this diagonal, up, and the other diagonal, right? So this cell also has 5 cells pointing into it, right? So we might be tempted to say, oh, this has a flow accumulation of 5. But, right, again, we have to look at what's the flow of accumulation of all these neighbors. Well, unfortunately, right, this cell right here also has flow accumulation, right? So now, in order to figure out the flow accumulation of this cell, we have to figure out the flow accumulation of this cell. And again, right, the whole point of this was we were trying to figure out the flow accumulation of this cell, right? It's that cascading effect where this cell's flow accumulation depended on the flow accumulation of this cell. This cell's flow accumulation depends on the flow accumulation now of this cell, right? So we're going to have to take this cell and say, what's its flow accumulation, right? And so if we look, right, it has this cell up here, this cell's coming in from the side, and this cell's coming in from the diagonal here. So this has actually 3 cells flowing into it, right? 1, 2, and 3. But we're still not done, right? These 2 don't have any cells flowing into them, but this one does, right? This one here still has its own flow accumulation that we have to account for, right? So we have to go one more time, right? What is the flow accumulation of this cell? Because we have to figure out the flow accumulation of this cell, to figure out the flow accumulation of this cell, to figure out the flow accumulation of this cell, to finally figure out the flow accumulation of the cell that we started with, right? So we're now 4 cells deep trying to figure out flow accumulation. So we're here. How many cells flow into this one? Well, in this case, it's just this cell here, right? Just this one cell. Now, what about this cell? How many cells flow into this cell? Well, we've already seen examples of this where there are no cells that flow into this cell. So this cell would get a flow accumulation of 0, right? Because again, we've looked at these examples. If there's nothing flowing into it, it gets a value of 0. Now here's the nice thing, right? Because this ends in 0 and there's no other flow accumulation going into this one here, we've now ended that cycle, right? We can now confidently go backwards to figure out the flow accumulation of everything else in the chain, right? We now know that this cell is not going to contribute additional flow accumulation beyond itself, right? So to put that another way, right, now we work backwards, right? So we know that this cell here flows into this cell here, right? That's one cell flowing into this one, and there's no additional flow accumulation coming from anywhere else. So we can calculate this cell here's flow accumulation, right? And we do that by taking the number of cells that flow into it directly, which is 1, right? This cell flows into this cell, plus any flow from the neighbors, which in this case is 0, right? Because there is no flow coming into this cell. It starts out empty, right? This flows into here for 1. This isn't contributing any additional flow. So we end up being able to calculate the total flow accumulation for this cell here as 1, right? Because we have the 1 cell flowing into it directly, and nothing is coming from cumulative flow. So we get a total of 1, okay? But we're not done yet, right? We have to work back up the layer because our end goal, remember, was this cell up here, right? So we know this has a flow accumulation of 1. Now we work backwards again and we say, what's the flow accumulation now of this cell here? Right? I encourage you to pause the video for a second, think logically through what we just did in terms of bringing over flow accumulation from the previous neighbors, plus the direct flow into it as well, and see what you come up with. Okay, so what we're going to do is we're going to take the 3 cells that flow into this one directly, that's 1, 2, 3, plus the flow accumulation that any of them would be bringing. And as we know, this cell here has a flow accumulation of 1, right? We were backtracking all the way down to be able to get that flow accumulation. So this has a cumulative flow of 1. So we're going to take the 3 neighbors that are flowing in directly, plus the 1 cumulative flow coming from the flow accumulation of the cell flowing into it, for a total of 4, right? 1, 2, 3, plus the flow accumulation from this cell that we calculated previously, for a total of 4. But we're still not done, right? Because again, we're going backwards up to try to figure out what this cell is. So now we know the flow accumulation of this cell is 4. What about the flow accumulation of this cell? All right, again, pause the video, see if you can work through this on your own, given what we've already done. So let's think through what we got, right? So for this cell, right, we've already stated that we have 5 cells. 1, 2, 3, 4, 5 that all flow directly into it, right? So we have 5 cells flowing in directly. But then we also have to take care of the cumulative flow coming from the neighbors, right? And so we get the 5 coming directly, but we also have to account for the fact that this neighbor actually had flow already with a value of 4, right? So the 5 neighbors directly plus the 4 from this neighbor already having flow gives us a total of 9, right? So this 9 is these 5 cells directly plus the flow that was coming in from this cell here, okay? We're still not done. We're almost done, but not quite, right? We're finally back where we originally started. We're back at this cell up here, the thing that started this cascade in the first place. And now we should have enough information to be able to figure out what its flow accumulation is. So again, I would encourage you to pause the video, think through what it should be, and then we'll walk through the answer together. Okay, so what we've got when it comes to this cell is we have the 5 neighbors that were originally flowing into it. This was the first set of 5 that we identified, just like we've always done, right? Anything that flows directly gets counted. And then we have to, again, worry about the cumulative flow from the neighbors, right? In this case, 0, 0, 0, and 0, right? But we've been backtracking, so we know that this cell here is bringing the cumulative flow of all of these pixels, right? Its flow accumulation is 9. So we're going to take the 5 flowing in plus the 9 from this cell to give us 14, right? So the flow accumulation of this cell is 14. Hopefully that makes sense. Okay. So what we can do is we can take that process and apply it to every single cell in the raster. This idea of figuring out how many cells flow into that cell. So what I've done is I've taken that process we just went through and I did it to every single cell in the data set. Right. And so as an exercise, I would encourage you to pause the video and figure out why this is 21. Maybe try to figure out some of these down here and how they were calculated. But again, right, the idea here is that we were able to take, based on the number of neighbors flowing in and any accumulated flow coming through those neighbors, we were able to calculate a final flow accumulation. So, just to be absolutely clear about what we've actually done and what the values of the flow accumulation layer mean. The value of a flow accumulation layer for any given cell is a count of the number of cells that will eventually flow into it. Right? And that's the reason why we were carrying over the neighbors' flow accumulations. Because we said, okay, not only are my 5 neighbors going to flow into me, but also all of the things that were already flowing into my neighbors are also going to flow into me. So we cared not only about our direct neighbors, but also everything that was flowing into them. And by doing it in this way, what we get for our flow accumulation layer is the number of cells that flow into a given cell. So we have an example here on the screen, but I want to talk about a different example. So for example, down here, this 9, right? What this 9 is saying is that there are 9 other cells in this raster layer. There are 9 other cells that are going to end up flowing into here, right? We don't count ourselves. So there are 9 other cells that are going to flow into here. And this flow accumulation layer and the fact that we're counting the number of cells is going to be very important for the next step, which is going to be taking this flow accumulation layer and converting it into streams. So the last step that we were going to talk about, right, because we said there was 3 steps. Create the flow direction raster, convert flow direction to flow accumulation. Now we're going to take that flow accumulation and we're going to create an output. And again, for the sake of this lecture, the output we're going to focus on is generating streams, which streams are basically just a way of saying where are things going to flow across the raster. You can think of streams as being rivers, right? For a good example of how would water, right, organize itself to flow in rivers. And so in order to take the flow accumulation raster and convert it to the sort of idea of a stream is going to basically be done in 2 steps. The first step is going to be to figure out a threshold for what we're going to call a stream. And we're going to talk about what that means in just a second. And then we're going to basically do a reclassification of this flow accumulation raster based on whatever threshold we come up with to create a binary output of 1 for is part of a stream, and 0 for is not part of a stream. So how do we determine a threshold for what is considered a stream, or what does that mean? So generally speaking, what will happen when you're trying to determine a threshold is you're going to have, based on the landscape, the soils, different aspects of the landscape, you're going to have in the back of your mind some area, and by area, I literally mean area, right? A physical size of space over which water would have to accumulate for there to be enough water for it to actually start to flow, right? And you can think of things like soils would impact this, right? Water tends to evaporate or percolate, meaning go down at different rates depending on the soil or concrete, right? What kind of surface you have. So based on these concepts, right, you're going to pick a threshold saying, okay, if this cell is experiencing this area of drainage, it's likely to start to be a stream. Okay. So then once you have that area in mind, what you can do is you can then figure out what cells meet that criteria, or what you would have to do for a cell to meet that criteria. And there's two ways you can do this. The first is to multiply the flow accumulation by cell area to give you the total number of area that is being drained into a cell. And that would allow you to directly compare your threshold to the cell values. But this is an extra step and it's not overly helpful. Instead, what you can do is you can take the area that you have in your mind, right? This drainage threshold area, and you can divide it by the cell size of your raster to figure out how many cells you need, right? So instead of converting from flow accumulation to drainage area, you can convert drainage area to flow accumulation. And just to be clear, we'll talk about in just a second what that equation looks like. Right. So let's go ahead and go through an example. Given everything we've done up to this point, we have an area, and we're going to say that a stream will form in our area if the upstream drainage is greater than 2,000 square meters. Right. What this means is that for a cell to be able to contribute to a stream, meaning that the water is going to flow rather than just dissipate without flowing, it has to be experiencing drainage from an area greater than 2,000 miles. Okay? So what we need to do is we need to take this area concept, right, this drainage area concept, and we need to convert that to essentially the number of cells that would have to flow. Which, again, if you think about it, right, the number of cells that have to flow into a cell, that's flow accumulation, right? And so we can figure out, right, what our flow accumulation would be by taking the drainage area, right, that threshold that we came up with, and dividing it by the area of a single cell in the data set. Okay. And then because you can't have half cells, we would just take the ceiling, right? And ceiling is just a fancy mathematical way of saying round up, right? Because you always want one more. So if it takes 2.5 cells, you would need to provide 3, right? Because if it takes 2.5 and you provided 2, that wouldn't be enough. So you always need the most. So ceiling is just a fancy way of saying round up. So you're always taking more than you need, not less. So basically, to reiterate that, right, ceiling of 2.1 would be 3 because you're rounding up every time. So if we take this flow accumulation equation and we apply it to our example here, right? This 2000 is coming from the drainage that we set up in our example. This 30, or the cell area, is the same as the area of a cell, which is the same as the square of the cell size, which is the same as multiplying the cell size by itself. So this cell area is the same as 30 meters times 30 meters, because for our example here, the cell size for everything is 30. Right, and so if you do the math on that, right, 2,000 divided by 900, and then you take the ceiling of that, you end up with 3. So what this means is that in order for a cell to meaningfully contribute to a stream, it has to have a flow accumulation value of 3 or higher. Right? This is the minimum flow accumulation that would be considered a stream. So once we have that threshold that we just calculated, the next thing that we have to do is take that flow accumulation threshold and use it to reclassify our flow accumulation raster to a value of 1 if it's greater than, which means it's a stream, or a value of 0 if it's less than that threshold, meaning that it's not a stream. Okay? And so we've already looked at examples of doing reclassification when we were talking about suitability models. But I want to walk through it again just because I think it's really important to have a really solid understanding of some of these fundamental concepts like raster reclassification, because it comes up again and again and again across all kinds of analyses, right? And so what we have to do is we have to set up a reclassification table where we have a lower limit and an upper limit for each value that we want to reclassify into, right? And given that our example here, that anything 3 or greater is considered a river, what that means is that anything less than 3, which for our data set goes from 0 to 2, right? Anything less than 2, anything 2 or less is not considered a stream, meaning its output value is going to be 0 from the reclassification. Anything 3 or higher, which in this case, right, the maximum value we have for flow accumulation is 21, right? Anything 3 or higher would be considered a stream and given a new value of 1. So what I want to do is I want to go through again, I want to kind of make sure we understand how this reclassification works. I want to go through some examples of reclassifying values. And as always, it's a good idea to just start at the upper left-hand corner and see what you get. So our upper left-hand corner here, the actual value from flow accumulation is 2. So if we take a pixel value of 2, apply the reclassification table to it, what is the result going to be? Pause the video, think through how reclassification works, and hopefully you come up with an answer. Right? It's going to be 0, right? Because 2 is in between 0 and 2, right? Because if it's equal to the upper limit, it still goes in this class, right? So 0 to 2, well, a value of 2 is going to be equal to 2. Therefore, it's going to have a new value of 0. Okay? So let's go ahead and do another example here. What about this value, 14? Right? If we have 14, if we have a flow accumulation of 14, we apply this reclassification table. What is our output going to be? I want you to pause the video and think through what you think we're going to get. It's going to be a value of 1, right? Because 14 falls between 3 and 21. Therefore, it's going to be mapped to a new value of 1, meaning that this 14 here is considered a stream in the reclassification. Let's do one more example. What about a value of 3? Right, so this sits exactly on the line. Right? Our threshold was 3. Well, this has a value of 3. So what are we going to get when we do that? Well, right, we can look at our table again. Right, so here, right, 3 is the lower limit for the new value. Right, because again, we set it up saying 3 or greater, meaning 3 was included in the stream values. Right, so because 3 is included, right, a value of 3 is going to map to 1, meaning our flow accumulation raster value of 3 is going to be reclassified to a value of 1, meaning that it would be considered a stream. Right, and so we can apply that result, the reclassification, to all of the pixels. I encourage you to pause the video, confirm for yourself that you agree with what we got. But you're going to get something that looks like this, where you have a couple of ones sort of going like this, and you have a couple of ones going like this. But by and large, most of the data did not have a sufficient flow accumulation to be considered a stream. Right? A lot of them had 0 flow accumulation, and there were a couple that had 1 or 2 that just weren't high enough to be considered a stream. So what we can do, just to sort of visualize our results, is we can take our binary reclassified table and then we can color code it. And you can see that we have a river that flows like this, and we have a river that flows like that. And it's a little bit easier to see color coded as opposed to binary numbers. So hopefully that made sense. What I want to do is I want to just end this video by going back through and just highlighting at a high level what we did to get here. Right, so just to remind everybody, when we started, right, we had a DEM, which is an elevation data set, where each pixel represents the elevation of the area underneath it. By calculating from a given cell the slope to all of its neighbors and finding the most negative slope, we were able to apply coded values to create a flow direction raster, where the cell value tells you what direction you leave the cell in terms of flow, in terms of fluid flow. We were able to take that flow direction raster, and by accounting the number of cells that would flow into a given cell, we were able to convert flow direction into flow accumulation. And then given flow accumulation, right, we were able to develop a threshold based on, in this particular case, a given area that we figured would be necessary to propagate the generation of a stream, as opposed to fluid that just wouldn't really meaningfully flow. And once you had that threshold value, you could apply a reclassification, and that reclassification would convert from flow accumulation values to whether or not, in this particular case, the pixel belonged to a stream, in the case of a value of 1, or not a stream, in the case of a value of 0. And what you would do after this is you could convert this raster to a vector. So you would have lines that represent streams, and you could do some additional visualization and processing in terms of making ordered streams so that you know which streams are bigger than others. And generally speaking, vector data gives you better visualization in terms of being able to do different colors and different line widths and stuff like that. But in order to go from a DEM we started with to a stream, we went from the DEM to flow direction, from flow direction to flow accumulation, from flow accumulation to streams. So hopefully that workflow makes sense. The intricacies and how everything works makes sense. And as always, if you have any questions, please reach out. Thank you.